start.
Thank you very much, Aminath, and thanks for the invitation to come and speak with you. Yeah, I think this is a really, as I was saying before we started, I think this is a really interesting group. You know, I love that it's led out of maths and stats, and I love that it's got the AI flavor. So today I'm going to talk about some work that I primarily didn't do. You know, there's a lot of names here, and I was one of the one of this supporting crew here. The guts of this work was done by Cameron Zackerson, who's a postdoc at Melbourne Uni. And I was really lucky to be involved with it, and to help out and have a lot of great discussions with all these really cool people on this slide. So the idea of this project was basically taking advantage of a fun new data set that we got access to last year, which was a data set from Facebook on mobility data. So the primary social media data that I'll talk about here is Facebook data. If we have time, we'll talk about some other applications of social media data, but we'll focus on the Facebook stuff. So yeah, so I'll give a shout out to ASIMS here, who support me throughout the last 7 years. Also DSTG paid for us to build a little app to actually map and show some of this stuff as well. So it's a nice bit of work that involves Tobin South, who's now at MIT. Okay, so before I talk about that, I'm going to take a little bit of a digression, a little bit of a diversion, or maybe this is kind of a provocation here, because as I said, I haven't been able to make it to many of these seminars, but I've watched all of the speakers. Emails come up, and I've looked at the YouTube channel and seen who people are in this community. And it's a really interesting community, I think, because it's kind of broad and it cuts across machine learning and AI and traditional mathematical modeling as well. And in the rest of my life at the moment at work, I'm sort of invested in thinking a lot about data science, and some of the people here who know me will know that my main business is data science, and I'm also been redesigning some master's degrees in data science at the same time as master's degrees in machine learning are being redesigned. And we have an institute for machine learning at my university. So I'm really interested in this question of what's the difference between AI and data science and machine learning, and trying to distinguish all of these things. And so a seminar called AI4Pandemics is a perfect place for me to sort of think about that question. So my question here is, what's the role of AI for pandemics versus data science for pandemics, and versus machine learning for pandemics versus mathematics and statistics for pandemics? So to do that, I have to think about, what do I think is the difference between AI and data science? And I've kind of written that on the slide here. I sort of see AI as really being a coverall term for a range of different techniques in machine learning and optimization and mathematics. Things. Yes, the joke in the chat that AI gets VC funding is a good one, and that's and you may it's a good argument to say that we should call things AI for pandemics to catch everything there, because that's the term of the moment. And both of these terms are sort of not clearly defined in a lot of ways, and they don't quite exist as disciplines yet. So I think this is an important thing for us to still think about. So yeah, I see it as involving lots of really big data and really heavy compute a lot of the time, whereas this is very opinionated, but my view of data science is, of course, data focused, and a feature of this study is going to be the bringing together of some different types of data sets together. I always see it as having a very statistical or mathematical core, and the data science applications that I'll talk about here have these very simple mathematical models sitting behind them. And a key thing tends to be, it sort of starts with a question, and then we go find a data set that tries to answer that question. We try to support some decision with it. But, it's like AI, it also covers lots of different techniques, including machine learning. So the provocation there is, what's the role of each of these disciplines in understanding pandemics? So, this is sort of, in my head, the canonical picture of what data science is. It's quite old now, it comes from 2013, from this famous blog post by Drew Conway. And, I really like this idea that data science sits at the intersection of maths and stats, the sort of core traditional applied mathematics that I came from and that some people in the audience came from. Computer hacking skills, so the computer science side of things. So increasingly over the past few years, I've learned more about this red part of the Venn diagram, and so got it into the machine learning data science area. And then I see it as being an enabling discipline that tries to answer questions that are outside of data science, that are in pandemics or are in health or in some other type of discipline. And brings data and machine learning and statistical tools to those. Where AI sits in this Venn diagram, I tend to think of AI as sitting at the top of this Venn diagram, sort of pushing outside of the machine learning part of the Venn diagram. It has lots of applications in different areas. But yeah, I mean, I see it as a more theoretical arm of machine learning. I've also made my own sort of, to try and crystallize my thinking about this. I've sort of made my own Venn diagram, my own another opinionated diagram of the relationship between these different fields. I tend to think of the stuff that's AI, but that doesn't count as data science, as being your chess playing robots and things like this. So your reinforcement learning that solves these games and things like this. It's not necessarily applied maths or applied to some discipline problem. So our group here is, I'm in a school of mathematics, so I made this slide thinking about our mathematics, our applied mathematics and data science group at the University of Adelaide. So I think about these disciplines as sitting like this, and the first apology that I'll give you in this talk is that this is totally not AI. If you take this sort of picture of AI as being really huge data, really sophisticated algorithms, learning to play chess and Go and things like that, doing deep learning, reinforcement learning and stuff like this, it's totally at the other end of the spectrum. So this is very much not an AI for pandemics talk, and it very much is a data science for pandemics talk. So I'll make that apology straight up. There's also this notion that the final side comment is that I think that there is a brand of data science that is kind of Australian and that is very academic and research focused. So I think of the data science that we in this group do as a form of academic data science that is kind of an Australian data science in that it doesn't necessarily arise out of industry. Data science in the US very much arose out of industry contexts. And applying machine learning to industry problems. Whereas, what I see is that we all bring a research and an academic, mathematical and statistical view to this new interdisciplinary field of data science. We can talk about that at the end. Perhaps it's a good discussion for the group. And I'm going to illustrate some of this view of data science through the actual talk here, which is largely on Facebook mobility data for measuring social distancing and risk mapping. So the key thing about this talk is going to be, there's an interesting data set there. I'm going to apply some pretty simple mathematical and statistical techniques and combine a couple of different data sets and to develop something that hopefully supports some decision making around COVID. we probably won't get to talking about Reddit for symptom extraction, which is a more machine learning, closer to AI sort of application. But you can ask me about it later. Okay, so what's the data set that we looked at? So as I said, Facebook actually has started releasing some privatized aggregated forms of mobility data. So for some subset of people who have Facebook installed on their phone, they'll have location services turned on all the time, which essentially means that Facebook gets the locations of like everywhere these people go. So that's a very small percentage of Facebook users who use Facebook on their phone, 1% or something like that. But this is still a lot of people who are just providing Facebook with their complete mobility traces. And so from that, Facebook can derive a number of different products that they make available to us, and will make available to you too through their Data for Good program. So there's this data set on user movement. So the number of movements between pairs of tiles. So they grid up the world into these small 50-meter sort of tiles, or between local government areas during an 8-hour period. So the number of people who have gone from LGA 1 to LGA 2 in an 8-hour period and back. The proportion of people who stay put, who don't move outside of their local government area or move out of their tile. So the people who are staying home. So that's useful for measuring, lockdown, whether people are actually staying at home during lockdown. Changes in movement range. And then there was this one that I was really interested in, this colocation data. So that was the probability that users from 2 different local government areas were in the same small region in a 5-minute interval. So at the start of the pandemic, when we were talking about close contacts, the probability of people coming into close contact with each other, this seemed like a really potentially useful off-the-shelf piece of data that Facebook was going to make available. I needed to think through what this colocation data means. I was quite taken with it. So here's a little example of what it means. So imagine you've got 2 different regions, so 2 local government areas, and we've got 4 people in them and 5 people. And then Facebook splits up the world into all of these different tiles. So the tiles are not necessarily, it's just somewhere else in the world. It's not necessarily in the same local government area, in the same region. It's just somewhere else on planet Earth. And then the idea is that in the first 5-minute interval, if I had 2 people from each of these regions, from region I and region J, moving through this same tile, this is 50 meters by 50 meters, so it's a pretty small tile. If they pass through that tile in the same 5-minute window, then we link them in this bipartite graph, and we have another couple of people who have done that. Then in the next 5-minute window, if another 2 people, if these same 2 people here pass through the same tile again, so they go out and they come back through, then you have another count. Let's say that that happens again. So you can count up all of these, the 1 and the 2 and the 1 interactions passing through the same tiles, and that's what Facebook do. And they add up all of those interactions, and then they divide by the number of 5-minute intervals in a week. And so from that, you get a probability of people from region I and people from region J passing through these same tiles. So that's this co-location probability. So divide by the number of people in region I and region J. So that's cool. And to generalize it, I think this double sum is probably wrong. You have to sum over all the pairs I and J there rather than doing a double summation. But the way that you calculate, Facebook calculates these numbers, is the number of 5-minute intervals in which users I and J from 2 different regions, I and J, were co-located in some other small tile K, and normalized. And that's what they report to us. And they report this to us for every single local government area in which there's data, across the country, which is really cool. So it's a really nice data set. So they aggregate these things up all over a week. So you can derive a few quantities from that. And so I cracked on and started doing this. You can calculate the number of average contacts per person, so taking expectations here, using these colocation probabilities, so you can get some idea of how many people do you come close to in a week on average. And then you can sum that up over an entire state, over all of the local government areas in a state. So NS is the number of people in the state, the number of Facebook users in the state, and come up with some measure of the statewide or the region-wide number of contacts. And so this to me was really really interesting, because this was one of the first ways that I could think of. We were doing this work before Google and Apple and everybody else started releasing their mobility metrics, and it could come up with a measure of the average number of contacts per person for each different state. And the thing that we noticed, we started building these plots very early in the pandemic, during lockdown number 1, which is when these 3 lines are here. So, national lockdown, March, April 2020. This was a good metric for people staying at home, so it could compare the effect of lockdowns upon mobility. So when Victoria went into its second lockdowns, you could see the things start to tail off again. And this was the Crossroads outbreak, I think, in New South Wales when they locked down again. It's significant that this period here, I stopped doing this around the end of last year. It's significant that's when I came back to work after a period of parental leave. So yeah, I kind of stopped doing this eventually. Also, by this time, everybody else was doing these lots of different measures of people's mobility by this stage from lots of different data sets, and people doing much more intelligent things than I was here. So Rowan Byrne from Melbourne Uni has got does one of the best efforts, I think, at combining a few different mobility metrics into a measure of how much people are moving around. So there are lots of different products out there. So that was one thing that we could do with the Facebook data, and it kind of works, and it's a good thing to have in the mix, I think, for measuring the effect of lockdowns. But the other thing that I want to talk about is this risk mapping. So the first data product that I told you about there was this movement data. So just looking at the number of people who are moving between regions. That's a pretty useful data set. And then what Cam did, so this was really Cam's idea, was to build a really simple mathematical model for mobility-based risk. So if you have some prevalence vector, so you say how many cases there are in a region, so you build a vector of all of your LGAs, put a 1 where you want to seed an outbreak, right? So you can do some scenario modeling here. You have that. Then Facebook gives you this movement matrix, M, essentially. So that felt a lot like a transition matrix in a Markov chain to us if we rescaled it. And then, so that's essentially what we did, was sort of treat this as this movement matrix, a rescaled version of it, as a transmission matrix in a Markov chain, and then propagate that, that one infected case from this prevalence vector around. So we got some notion of risk. That's it. That was the model. So in terms of data science, what we were doing is taking an interesting data set, asking a question like, where is an infected case likely to end up, and then propagating it around in the simplest way that we could, in the most sort of simplest but principled way that we could. So we did a few case studies for this paper, which you can go and look at. So the first was in 2020. You may or may not remember the outbreak at Cedar Meats, a meat packing factory in the sort of western suburbs of Melbourne. And we sort of looked at risk associated with that. So it was, a bunch of secondary cases from that outbreak. So here's a couple of different things. So the left picture here is people's movement into Brimbank. There's the Cedar Meats factory was located in the Brimbank LGA. From Facebook, we could get this idea of where people were moving into this region from. So some idea of the transition matrices. On the right, we've got data from the ABS. So we've got the proportion of meat workers who live in each LGA. So in the eastern suburbs, not so many meat workers, far more in the western suburbs and close to the meat factory. And so what we did was we had the Facebook data, which could tell us where people were likely to move. We had some idea of the number of proportion of meat workers in each of these LGAs, and we combined these two data sets. So the data science here was using a couple of kind of disparate, differently collected data sets and combining them together. So essentially what we did is we did this using the Facebook data. We looked at if there was if we put a case in Brimbank at the meatworks, which is where the star is, where was risk likely to go, and we could come up with this, and then we would correlate that with where we ended up seeing cases. So yeah, that's this plot here. I'm plotting the correlation of risk in different regions with the number of cases that we saw in the following week. And then that gave us decent correlations there, which indicated that this was reflecting reality pretty well. We found that things improved when we actually incorporated the fact that the people who were likely, if we want to look at risk, the most risk in this outbreak was going to be to meat workers, because they were people who were coming in contact with infected cases in the meatworks. So when we multiplied these results by the proportion of meat workers in each LGA, then these correlations actually improved, and so there was some better explanatory power of this pretty simple model of which LGAs were likely to see outbreaks based just due to mobility to people, where people were likely to go. That was case study number one. Case study number two did a similar thing in Sydney with the Crossroads Hotel outbreak. So it was a pub where there was an index case and lots of people got infected from that, and then seeded them elsewhere. Producing, there was not ABS data to use there. It wasn't so cleanly localized to some particular profession, and the ABS doesn't count people who go to pubs, I guess. But we could produce these mobility-based risk estimates and then look at where cases appeared in the coming weeks during that outbreak. And you can find, and we would see that there was a decent correlation here, which got better as time went on, as more cases appeared, and there was more sort of circulation from transmission. So that was another nice case study that showed that this sort of had some good explanatory power. The last case study was not about an isolated outbreak. This method kind of worked well for the case where you have one centralized outbreak, so you can put a 1 in this prevalence vector and then look at mobility as where it spreads out to. So really seed an outbreak in one location. Things get a bit more complicated when you have community transmission, so you sort of have cases popping up all over the place, and then they're mixing around. So this prevalence vector is not so simple. You have multiple entry points which need to be sort of flowed around by this sort of Markov chain approach. So this is what we tried for the start of Victoria's second wave. in mid 2020. So the left panel here is showing you at a particular point in time where there were active cases. And then the second panel, and that's and this panel up here. Let me just step through it and take a few minutes to step through this in this format. So the left panel here shows you incident and active cases. The middle panel shows you our risk estimates. And then there's a difference between these two things over here on the right. So we've got the number of active cases at a point in time, and this obviously changes over time. And then this panel at the top, the heat map, is showing you the correlation between the number of cases at time t, which is along the vertical axis here, and then the number of cases that there were at some future time t prime along the horizontal axis. So these heat maps are filled in the bottom right corner because that's the way that time propagates. Up here would be correlating with cases in the past, which is not of interest. So we only look down here. And so this point, for example, is on the date, the 5th of June, the correlation between the number of cases on the 5th of June and the 15th of July, for example. So in darker colors are a higher correlation. So when there's lots of community transmission, the number of cases today is pretty well correlated with the number of cases across each LGA tomorrow. And at the start of the outbreak, things are a bit more popping up randomly all over the place. So you should expect there to be darker colors up here. Similar with these risk estimates. So we're kind of looking at the correlation between risk estimates at a point in time and then a point of time in the future. So again, when there's lots of community transmission going on, you should see that the distribution of cases today should look similar to the distribution of cases tomorrow across LGAs. And then what's interesting is the difference between these two things, which sort of shows you how much predictive value you get from this risk mobility-based risk estimate on top of a very simple predictive model that just says number of cases today is number of cases tomorrow everywhere. And then what we saw is when the outbreak, up in the top right here, when the outbreak is in full swing and there's lots of community transmission going on, well, there's just a lot of COVID everywhere. It's all mixing all over the place all the time. So there's not much extra value gained by knowing the mobility patterns, knowing where people are moving around. Similarly, for the most part, early on, when cases are popping up randomly being seeded everywhere, you don't have a lot of predictive power. You do have some pockets here, right? So when there's a certain decent number of cases, I don't think it's necessarily a coincidence that you get some value about from knowing where people are likely to move to based on mobility patterns. This sort of slightly darker period here is saying that making early predictions based on mobility is a useful thing to do. So knowing people's patterns of mobility gives you some sort of early value in predicting if this outbreak is going to become widespread. It's going to be dictated by people's mobility patterns, and so having that information is useful. There's a question. Let me take this question in the chat. Did you find two regions that are not geographical neighbors but are mobility neighbors and see how transmission occurs? Yeah. Okay. So so were there cases here where places were connected together in a sort of network sense, were close in a mobility network sense, but not necessarily geographically? The answer to that is yes, although what you see with these mobility matrices is they do tend to be diagonally dominated. You do tend to see mobility between neighboring LGAs, because of course you do. Some things that you saw, if I go back to Melbourne here, the center of the city would be a hub for mobility a lot of times. So yes, you could definitely see cases where everybody commutes into the city from far away. So we definitely saw effects like that, sort of a gravity model type thing. Yeah, so the network was certainly important, but the network tends to align with geography pretty well as well. So what we did with this, so the nice other part of the nice other data science aspect of this was we made an app. So we actually used some of this to help with some DST group planning. They wanted to have access to this methodology as a tool that they could run scenario modeling and stuff on. And we built that app. It was great. It looked really pretty. Tobin South made it. This is what the app looks like right now. You can go there and you can see this error message yourself, because the learning here was that when you have that it's a bad idea to have data that's hosted at one place and that needs to be accessed in another place, and that databases and web apps and things are hard. So because this is an app that had to communicate with data that was stored at the University of Melbourne, the university's firewall got in the way, and I learned a lesson to not promise to make apps for people anymore, but to subcontract that out. But there was this decision support aspect to this work, and one day we'll fix the firewall and I'll show it to you again. Okay, so I'm going to wrap it up there. I'm a tiny bit short, but that's okay. And I want to bring this back to where I started with this, was this notion of data science versus AI. So I've talked about this case study here of some data science techniques and an interesting data set applied to one problem in the pandemic. And for me, part of the reason to talk about this particular study, particularly when it's mainly not my work, when it's mainly Cam's work, is that it's a really good illustration, I think, of data science, what I guess I see as data science aspects applied to the pandemic. So, mathematical modeling has certainly had a moment over the past year and a half, and it's been pretty clear value in shaping our pandemic response. But I think this is a place where there's been some use for, what I would term as data science, right? A key feature of this work was we combined a few different data sets together. So it's just ABS here and Facebook, but you can certainly see how multiple different data sets, there's some of which are novel, can be combined here. I can talk about one aspect that I see and that other people see that distinguishes data science from machine learning and from these other disciplines is this notion of modeling. And so there was certainly a mathematical model for mobility that sat behind this. It was a Markov chain. It was the simplest possible mathematical model that you can come up with, but there was some mathematical model in there. Also, I digressed and talked about these colocation probabilities deliberately as well, because there was some math in that, or it's not high level math, but there was some need for sort of probabilistic thinking and being able to write down these expressions and understand how you got probabilities out of counting these curious things. So the data science there is applying some simple mathematical techniques, but some mathematical literacy and some data literacy to the data set. There was this key aspect that was like getting insights from the data, how much juice is there in the data. And one key thing is that, these models were all really explainable. We didn't try to eke too much out of the data. So it had this notion of this sense of trustworthiness, at least to me. So the discussion question here is, what's the role for AI in a project like this? I can see, and I'm sure that you'll be able to see, there are many more data sets that we could apply and that we could bring into this risk mapping problem. I've used the simplest possible predictive model that we could possibly use, but what will be the value of using more sophisticated machine learning models to do some of these predictions and things like this? Of course, if you do that, if we apply a more sophisticated model, you start to lose some of the explainability, some of that trustworthiness. And I do wonder just how much more juice is there to be eked out of these things like these mobility data sets. So there are places where this can go. Yeah, it's clearly not an AI4Pandemics project. It was a data science for pandemics project. But yeah, I hope that was interesting. And I'm happy to take some questions from people.
Thanks, Louis, for the great talk. Is there any questions from the audience?
You can use the chat too if you're scared to talk. I'm adept at monitoring the chat now.
Can I ask a question?
Mm-hmm.
So when I see a project, I first ask who is the stakeholder. If the stakeholder is the government, they have access to like phone towers. I don't know if they have access to that or not. Or have you explored access to such data in an anonymous way? Or because that one is much better than Facebook, right? If they can use it, if they want to, I don't know if they can use it or not. So that's the question. What benefits do the stakeholders get from this project?
Yeah, well, I guess there's a number of things to say there. I mean, whether the government has access to mobile phone data, I don't know, actually. I mean, they probably don't. Like Telstra is a private company and Optus is a private company. So at least when working with defense, so working with DST group or something, no, you totally don't have access to that because, they're mandated to not surveil Australian citizens and stuff and things like this. So at least with the defense sector, our value to them is that being in academia land, like we can get access to data sets that they can't easily get access to themselves. Like they have their own bureaucracy and things that make it difficult. As to whether mobile phone data would be better, yes and no. I mean, there's heaps more people with mobile phones than there are people with Facebook installed and location tracking turned on all the time. But what's the data that you get from mobile phones? I mean, unless you've installed Safe Blues or something like this and are getting really sweet data there, you've got data from cell towers, right? You know which cell towers have been pinged. So you don't, and that sort of resolution of, how many cell towers are there around me, like one every 20K or something like that. So you don't necessarily have like super high resolution data, certainly not at the scale at which these Facebook, 60 meter by 60 meter squares that Facebook has providing this stuff. So yeah, I think that, so that question is not as clear cut, I think. As for working, certainly the government can get access to more data. So particularly the line data for case numbers from COVID. Certainly, they were providing that data, so good data that was beyond what you can get from COVID-19 data.com or something on case numbers and details there. But yeah, it's hard to work with. My answer to your question is it's complicated.
Thank you very much. Thank you. Very interesting work. Thank you.
Thanks, Ash.
Yeah. Any more questions?
I might make a couple of comments if that's all right.
Yeah.
Thanks, Lewis. So yeah, that was an interesting talk. And I guess as a long-time AI researcher, I can't resist making a few comments.
Yeah, good. I'm glad.
I mean, actually, I kind of agree with a lot of the way you kind of categorize data science, and particularly the way it's done in Australia. I don't really have any problems with that. I think maybe something that AI has, at least from the public's point of view, there's a big perception, I think, that, and I guess it's true, right, that AI, something that AI has is this, I don't know, there's some sort of expectation about a greater level of autonomy and independence in AI systems being able to make decisions by themselves. So sure, they do prediction, but then something is done with that prediction, right? And then that gets fed into something else, and then something else happens automatically, and all of a sudden your refrigerator has ordered you a whole bunch of groceries and you charged it to your credit card or whatever. And, you know, obviously there's huge concern when it comes to things like autonomous weapons and killer robots and all this sort of stuff, right? So I think that's, I don't know how, I'm interested to know what you think about that as well. I think it's this sort of extra level of autonomy that perhaps statisticians and data science didn't have to deal with. What do you think?
I think that's right, and that's probably a good distinction. Yeah, like I think of, I guess like reinforcement learning as a sort of example there, where you can, the sort of constrained example where you sort of go further and further, and there is some sort of, and you have this notion of complexity as well, where you're sticking things get stuck together, and some decision making and stuff gets automatically made. I mean, a question for the group is, what role does that have? Has it had, or can it have in pandemic response, I guess, right? Like there's this, you get into this question of responsibility. To me, like data science feels like it's very much human in the loop still. And it's insights to support human decision making, which has still got some legs, which is something that is distinct from something closer to fully autonomous artificial intelligence and decision making. I wonder where this goes, but in the context of pandemics and other areas as well. So I think I agree with your characterization. I hope that I think these two things are distinct, at least in my head, and they both have pluses and minuses and purposes. Whether the public sees these things as being distinct, or whether we can describe that difference well enough, or whether data science gets subsumed into AI, which gets subsumed into whatever the next phrase is, I don't know. But this is an interesting thing, an interesting exercise, I think, for us to try and define these things as academics and as researchers. I think you're correct there, by the way, about Optus mobility data. Yes, they'd certainly derive these products, these mobility products, and government and everyone else has access to them as well.
I mean, it's interesting to think about, if how much would people be willing to, or like at what point are people willing to allow a company or an app or whatever to track their location with sort of high precision, if they're supposedly going to get some benefit out of this, like if the app's going to warn me that I'm wandering into a COVID hotspot zone or whatever, don't go to this supermarket because there were a bunch of people here this morning or whatever. Would that be enough for people to to sort of jump on board, and how far does this sort of thing go? You know, we straight away get into all sorts of questions about ethics and privacy and stuff like this. By the way, I'd have to say AI researchers are not the right people to answer these questions either, because we don't know the answers to such things. But somehow it's now at the doorstep, and I think we need to start talking about this. So
yeah, totally. I mean, there's an interesting question just in the data set that I've talked about here related to privacy, right? Like, people are giving up this data. You know, there's thousands of people who are represented in this Facebook Data for Good mobility data set. It's all okay, and most of them will be happy with it, I think, because there's no way that you're identifying a person here, and there's noise added to small numbers and things like this. So it's all cool. I don't know that people have necessarily given informed consent. They're providing up this data. They've clicked it in the terms of service, and they've at some point enabled location services. Do they know that their data is being used by this? Probably not. It comes down to like, it's sort of all fine if you anonymize the data correctly, right? And if it's appropriately privacy preserved, and I believe that is the case with this data set. But it's like, how much do you trust Facebook there, right? Like the people who are responsible for doing that are Facebook. And so in some sense, like Facebook Data for Good is like really smart. Like it's a separate entity that is being pretty responsible with data and has seems to have some sort of brand differentiation from Facebook itself, almost. So they've done a good job there, and they're able to provide these genuinely useful, I think, data sets. But yeah, it's a whole minefield of questions about just people's literacy about data and how it's being used here and what's appropriate. And we also are not the people to answer this question. It's sort of like a whole of society discussion, I guess. Yeah.
Thanks.
Thanks for the great talk. I think can we all thank Louis for his time and talk? And it's a pleasure to have you here for the series. Thank you.
Thanks, everybody. This was great.
Thank you.